We are the Solar Commons team, and we are presenting the use case for Cheyney University. We have 3 different universities represented here. The University of Minnesota Twin Cities is our engineering team. We are comprised of mechanical engineers and electrical engineers. The University of Minnesota Duluth is our anthropology team, and the University of Arizona is our art team. We are supported by mentors like Catherine Milone, Ellen McMahon, Uwe Korchagen, and Carlito Miller Espinoza. Next, we'll go forward with our use case. So the introduction to Cheyney University is a historical Black college university with over 600 students. The goal is to eventually achieve carbon neutrality, which we are attempting to get to 100%. The critical load here is the new science center, which we want to provide resilience with a battery. And we have partnerships with Sonali Solar, Urban Farms, and Advanced Alchemy Labs. So our guiding principles here. For the Solar Commons, we partnered with Solar Commons Project when designing our system. They're a multidisciplinary research project at Duluth that applies a Solar Commons model of low-income community trust ownership to combat climate change and social inequality. This model works in gathering the common wealth of the sun and monetizing the savings in a social wealth fund, and then distributing it through local peer-governed community trusts that support regenerative local projects. So this model matches philanthropic organizations for projects to finance the system, and our partners at Duluth look to partner with the William Penn Foundation to fund a section of our solar system, which locks in a set rate of payments for Cheyney and benefits B. Anderson Elementary School in nearby Philadelphia. So for the art section, another part of Solar Commons model is that it's involved with the community, and public art is a large part of that. So our artist team from the University of Arizona designed this mural for B. Anderson Elementary School. This artwork incorporates symbols from the state of Pennsylvania, as well as visuals from the sun's commonwealth. And we also designed a solar pavilion to connect the Cheyney campus community with that. And next, I'll hand it up to Seth to continue with the proposal.
So to start off with, we have our system locations here. We have the north and south ground mount. We have 3 rooftops that we installed solar panels on, and then we also have a solar pavilion that we used. So to start off with, we have the agrivoltaics ground mounts. The agrivoltaics were used to strengthen Cheyney's relationship with the agriculture partners, Urban Farms and Advanced Alchemy Labs. Additionally, it gives you a dual land use so that we can grow crops, giving a communal benefit while also creating that power. Next, we use ballasted roof mounts. These have a 20-degree slope with 3-foot spacing between all the panels. They were used to avoid using up all the green spaces on campus, while also utilizing some of the empty roof spaces, so we can use that dual land use still. And then finally, we have the solar pavilion, which creates the communal space for students and faculty to gather, do some studying or to talk with each other, while also generating some power. For the system overview, we have 75% of the energy production coming from that agrivoltaic ground mounts, while 22% is coming from the rooftops. And then that small solar pavilion provides just 3%. And this system in total meets 61% of Cheyney's load.
Okay, now we're just gonna take you through a quick summary of each of our sites. So this here is the north ground mount system. It's one of our agrivoltaic designs. 470 kilowatts, producing 650,000 kilowatt hours annually. There's a little shading in that southeastern corner there, but after those panels were removed, we reach an annual solar fraction of 94%. This next one is our largest site, the south ground mount system, 815 kilowatts, producing 1 million kilowatt hours annually. Again, we had some shading to the east along that road where those trees are, but after removing some panels there, we reach an annual solar fraction of 92.5%. The solar pavilion, so again, this is a small system, only 32 kilowatts, producing 45,000 kilowatt hours annually. No real problems with shading on this one, but again, just creating a communal place for students and faculty to gather, sort of provided for within this solar design was something that we thought was important. Then going through our 3 rooftop mounts, this is the largest one of the 3. Duckery Social Sciences Center. It was 230 kilowatts, producing 318,000 kilowatt hours annually. We didn't really have any problems with shading on this one and reached an annual solar fraction of 98%. Ada George's Dining Hall is a 96 kilowatt system, producing 116,000 kilowatt hours annually. We had some shading issues with those trees in the northwest corner and some of the obstructions in the center. But again, after removing the panels that were affected by that, we reach an annual solar fraction of about 95% here. And then the last rooftop system is a 60 kilowatt system on Tubman Hall, producing 77,000 kilowatt hours annually. There's a little bit of shading with some of the obstructions in the center there, but after removing those panels, we reach a solar fraction of 96%. And then just quick, we wanted to highlight that we did look into Cheyney's future development plans. We got this picture from their site, and none of our sites interfere with their development plans. There's the north ground mount system. I don't know if you can actually see my cursor, but yeah, it's that field right above the Science Center. And then the south ground mount system is kind of hidden behind those solar panel picture, but they are planning to develop anything there, and the rooftop mounts are clear too. And I just wanted to highlight that this design does utilize the 360 watt panels from Sonali Solar. So ideally strengthening their business relationship and also taking advantage of the close partnership in sourcing those panels. Now I'll pass it off to Mariana to go over some of the economics.
So for the arrays that are not going to be under a solar commons agreement, which we'll get to on the next slide, we went with a PPA with an annual escalator of 2.5% to avoid a really high initial starting energy price and to utilize tax incentives. We took advantage of the federal ITC and MACRS, and since we'll be using both, the MACRS depreciation will be 87% of the project value. And then we did not assume Cheyney would be selling SRECs because then they would not own the solar part of their generation anymore, which could inhibit their ability to claim net zero in the future, but it would improve their PPA price. So for the solar commons agreement, the north ground mount and the solar pavilion will be under a solar commons agreement, which means Cheyney will pay a flat rate of 5.6 cents per kilowatt hour with no escalator straight to the trust. The money is taken out from the trust annually to cover the expenses for the sites, including insurance, administration, inverter replacements, and end-of-life decommissioning. So Cheyney does not have to pay any of this. The result is about $160,000 going to the trust over the lifetime of the array, and it saves Cheyney about $170,000 due to the electricity cost not increasing. These arrays would be paid for by a donation of $688,000, and that investment would result in an NPV of negative $546,000 due to Cheyney's low utility price. In areas with higher utility costs and higher demand charges, the NPV improves for solar commons agreements. And keep in mind that this NPV does not account for avoided public health costs or reducing greenhouse gas emissions. And finally, this is the overall economics. So our weighted average overall PPA price was 9.2 cents per kilowatt hour. And note that the solar commons arrays are the cheapest due to the solar commons agreement. The economics were maximized for each system by maximizing the solar access and optimizing tilt based on the system type. Cheyney's current electricity rate does not allow for net metering, and economic analysis showed that switching to a net metering rate worsened the economics, so we didn't change the rate. And the NPV of our design is about negative 2.8 million, assuming a utility escalation of 1.6%. As mentioned previously, we did not assume SRECs, but if we did, it would improve the NPV by about 170,000. And we moved forward with this size system because we wanted to maximize the solar and accelerate their progress towards net zero, and still keep in mind that this NPV does not quantify the impacts of climate change or improving Cheyney's reputation.
So some of the battery options we considered was a peak shaving battery and a resilience battery. The peak shaving would allow for some cost savings on the electric bill since we can't export to the grid. However, the resilience battery would help to protect those critical loads. For the peak shaving battery, we determined we would not move forward with it. Batteries we found cost between $400 and $750 per kilowatt hour. And for us to get to a 1% export, we would need a 14,900 kilowatt hour battery, which would be $6 million to $11 million, which we determined Cheyney would not want to invest in. For the resilience battery, we sized a battery that would cover the Cheyney Science Center load for 1 to 2 hours. We used Reopt Lite to model that, and we determined that if we had it connected directly to the solar arrays, we would be able to charge the battery when it's being not used, and then if it ever needs to be used, we can just charge it at that point. Additionally, we would recommend that in the future, they utilize an island microgrid system to allow to disconnect from the grid during an outage and then restart those solar panels to continue to produce energy.
Okay, so over voltages of 145 at transformer 0, 13, 24, and overloading at transformer 1. With the use of some smart inverter controls for subsystems connected to transformer 0, we were at best only able to reduce the overvoltage down to 1, but not completely 0. And we still found that overloading at transformer 1 was still prevalent. And then the next part, we found that the voltage profile of the distribution lines were still relatively flat, which is a good characteristic. And since we weren't able to completely reduce all the overvoltages and overloading in our system, we proposed a few solutions to try to mitigate those problems. The first one consists of some equipment and infrastructure upgrades, we're specifically looking at transformer upgrades. And then we're also looking at reducing our system down by removing a few sites maybe. And we could also try to increase the storage or try to limit the maximum PV power production. And we could also try to increase the local demand through campus expansion or something like an EV program.
So the construction schedule planned for the system would take roughly 4.5 months. This would include things such as pre-screening, just to make sure that everything is able to be constructed upon. The design, which includes structural engineering, system design, permit applications, and the legal process, all to make sure that the buildings are safe to be constructed upon, that the design is all ready to be enabled, and so that all parties involved are in agreement with this process. Next is the material arrival, which does overlap some with the design and construction phase. This is to make sure that they have materials to start building, such as excavators and the panels themselves. Finally, the construction process is using civil construction, system construction, and the electrical construction. The civil construction is where we flatten out the areas for the ground mounts, and then system construction is where the actual design of the solar construction of the solar panels is taking place, and then the electrical construction is where the panels are actually wired. Next, the commissioning is expected to take 14 days, and this is where the interconnection takes place, where the system is being connected to the grid itself. And finally,
you want me to send it to you?
Yes, send it.
and
We're not really.
take
This
place.
one, yeah, sorry for the interruption there.
And finally, inspections take place where the Thornbury Township inspects the system and makes sure that all the permits are being followed. Now, next, we have any questions?